Hey y'all, we're going to dive into part two of our survey of the nature of science here, and we're looking at some tricky business statistics. This is as far as we're going to go with statistics, and we will go a little farther in this class than most introductory science courses would go. But I feel that a simple knowledge of statistics is really helpful in our world today. Okay, so in essence, statistics will help you determine if data supports a hypothesis or not. It will help you determine how reliable the spread of data is. And basically there's two camps here. You can use two tools to figure out if a hypothesis is supported or not. You could put participants into different groups, like we talked about earlier with the 5-hour energy. Put participants into different groups and collect data from each group and come up with some sort of average of your dependent variable, and then see if the averages are different between the groups. In other words, is there any effect of the independent variable on the dependent variable? This is a very powerful tool. It's a tool that we don't always get to use because sometimes the subject matter of study is more complicated than this, where you can't just put things into discrete little groups and make nice measurements and calculate nice averages and figure out how they vary. A really good example of where we can't do this is like if we're going to study a population and see how the population changes in time due to some variable. That would be like a correlation. It's the same population, we don't have different groups, but we want to see how they're changing with different conditions, and we assess them through time. That would be something like a correlation. Or if you wanted to see how two different trends compare with one another, sometimes that can tell you something. Like we would do this for climate change discussions, where they talk about how you would look at a graph showing the CO2 level rising, and then you'd look at a graph showing the temperature rising, and then a lot of scientists would say it's the rising CO2 that's causing the rising temperature. Although I don't necessarily think that's something that we can really claim, for a reason I'll show you in just a minute. But those are like your two tools, comparing means and analyzing correlations. So we'll take a look at both of these here in this lecture. Okay, we'll start off with comparing averages. So to illustrate this process, I'm going to show a figure here from one of my publications. This is some of the work I did at the U, where I was looking at hearts, and what you're seeing is the cross section of the heart. So if you were to take a thin slice right through the middle of your heart, here's the two chambers of the hearts. We'll learn about those later in the class. But if I was to take a section of the heart and then stain it for fibrosis, so fibrosis is scar tissue, and the more scar tissue that a heart has, the more damaged it is. And that's what we did. And so you can actually stain these hearts to look for fibrosis, and then you can even, just using like a photo imaging software, have it count how many pixels are red and how many pixels are blue, and figure out what percentage of the heart is damaged due to fibrosis or scarring. We have normal hearts shown here on the left, and these hearts are ones that have muscular dystrophy to them. So you can see the individual with muscular dystrophy has much more damage to their heart. Okay, so let's imagine that I did this for a whole bunch of hearts, and each one of these data points, so here's my two groups. This data set is called categorical because I have two separate categories, and there's no overlap between these. Like there's no group in the middle that's half normal and half dystrophic. You have a very clear, discrete category of those that are normal, and a very clear category of those that are dystrophic. Okay, each one of these data points is a heart that was surveyed, and this is actually fictitious data, so this isn't the actual data from my publication. But if I was to figure out, okay, so I've got a heart here that's got only 2% scarring to it, it's not a lot of scarring. I've got one maybe with 3% and 4% and 5%, and I have one with 10% here. And then here's my dystrophic hearts that I studied. One's got 4%, and there's this big spread here in how much scarring they have. Well, what you want to do first is figure out what is the average scarring or fibrosis for each of these groups. That's what I'm measuring. Fibrosis here would be my would be my dependent variable, and I'm thinking that it depends on the type of heart that I have, whether it be normal or dystrophic. So dependent variable, independent variable. Okay, if I figured out what the averages were, it'd be something like around here. If you remember how to calculate an average, what you do is you add up all of the data points and then divide by the number of participants. So I would, take 2 plus 3 plus 4 plus 5 plus 10 and divide it by the number of participants. That would give me the average amount of fibrosis here. And this would be the average amount of fibrosis for this group. And you can see there's a whopping difference between these. This average, on average, the hearts in this group, they've got maybe about 4% fibrosis. So, a small 4% area of the whole heart is scarred. These hearts, if I look here, they have more like a 17% scarring. So you got an average of 4 compared to 17. There's a lot more scarring happening in the dystrophic hearts, at least from this data. Now, here's the caveat, a very important question. Can I trust this finding? Okay, this is a very notable finding, but is it trustworthy? That's what statistics will help you to figure out. The statistics will incorporate two things. Generally what we do on a stat like this is we do something called a t-test, and that will give you something that is called a p-value. And the p-value will tell you how likely the difference in averages is due to random chance. And generally, a lower p-value between averages means that the difference that you're seeing is more reliable. And the higher the p-value, the less reliable. Okay. So let's say this would be important because just take a look here once. Imagine it's Tuesday morning, okay, and I'm going in to grab some hearts out of the freezer, and I'm going to survey their fibrosis. And let's imagine I've got a whole freezer full of hearts. I've got 100 normal hearts in there. I've got 100 dystrophic hearts in there, and just on this Tuesday, I don't have much time. So I just grabbed a handful of dystrophic ones and a handful of normal ones. What if it was the case that in my freezer I had a whole bunch of hearts towards the back here, which actually had a lot of fibrosis in them? It was just a random luck of the draw, just because it's Tuesday morning and the more fibrotic ones, just by random chance, happened to be up closer to the front where I grabbed them, that I grabbed these. In other words, if I was to do this on Wednesday again, and in that day I actually grabbed those normal hearts that had more fibrosis, well, then you can see my average be much closer, right? Or the same for the dystrophic. Maybe on this particular day I happened to just grab these 3, which were the worst of all the hearts, and maybe much of them are more like this. They've got smaller fibrosis, and that would actually bring my average down. How likely is the difference we see due to a real difference in the world versus just random luck of the draw? That's what a p-value will tell you. And if you do a t-test, a t-test is something you can do easily now. In a stats class, you would learn the longhand way to do it. But now you could just go on Google and Google t-test calculator, and all you do is just put in all the data points for your one group, put in all the data points for your other group, and it will spit out a p-value. If p equals less than 0.05, we would say that the difference in the averages is statistically significant. In other words, it's very likely that the difference that we're seeing here is not due just to random luck of the draw. P of less than 0.05 means that there is less than a 5% chance that the reason these averages are different is just because of random luck of the draw. In other words, there's a better than 95% chance that the reason we see a difference in these averages is because of a real difference in the hearts. Okay, so the smaller the p-value, the more likely it is that there's a real difference between the groups. the higher the p-value, the less likely it is that there's a real difference between the groups. And that's going to be something I want you to know for the exam. Okay. You can imagine if I did this again, let's say, and I had all the data points in the one group on a really tight spread and all the data points on another tight spread, and I had more data points, that would be much more reliable data. That's much less likely that this data set was just due to chance alone. Okay, so the p-value is really going to be determined by sample size and sample spread, how far apart the data points are. Okay, not all averages are equal, and so if you really want to, like if you're looking at a magazine and it's showing you, like, let's say the average rating of colleges, and let's say they did some sort of survey and they surveyed students, and the U of M has a really great score, and St. Thomas has a great score, and another school has a really bad score. Like, most people would just look at that graph and go, oh wow, and just take it at face value. But a scientist would say, oh, I want to know how many students they surveyed, and I also want to know what the spread was. I want to know what the p-value is between those average, college scores. So that kind of stuff, especially in worlds that are not run by scientifically inclined thinkers, especially like if there's money involved, talking about bias, money is a huge source of bias. So if the research is funded by, let's say, the U of M, then obviously they would be, inclined to make the research be favorable through their school or something. Marketing firms, they're not inclined to follow the rigors of the scientific method and sort of the code of scientific ethics. And so oftentimes, any news article you read or anything that's not peer-reviewed, you would want to maintain a degree of skepticism there when you're looking at graphs that are just showing you averages of things. You want to know what the sample size is. You want to know what the p-values are. Okay? All right. Correlations to test hypothesis. Correlations are used when you want to assess more than maybe just two variables. Like maybe there's 3 or 4 or 5 different types of variables and you want to see how they relate with one another. We use correlations when it's really hard to have a controlled study. Remember, a controlled study is where you have different groups. You have one group that is one part independent variable, and you have another group that has a different independent variable, and another group with another independent variable. So again, back to our 5-hour energy. Remember, we had the one group of students that had no 5-hour energy, the next group that had more, and then the other group that had more. Okay, and remember, a controlled experiment is where there's nothing else different between the groups other than changing the independent variable. That's the only variable that differs between the groups. Well, there are some times where it's really hard to create a controlled study like that, and so then you wouldn't be able to have nice groups like this and clear-cut averages and means, but you can still use data to answer hypotheses in those situations. You would just have to use correlation data instead. Okay, and we also use this when we're looking at one population and how it changes through time. That's called a continuous data set. Anytime that there is meaningful data happening in between the data points that we just haven't captured. If there's a real data story happening in between the data points, and if we were to get out and make more measurements, we would capture that story. That's a continuous data set. So this shows different levels of correlation here. Here, remember that the dependent variable is always on the y-axis, and the independent variable is always on the x-axis. And so here we're showing directly proportional relationships between the variables, and these are inversely proportional relationships. Here, as I increase the independent variable, it looks to cause an increase in the dependent variable. Here, if I increase the independent variable, it seems to decrease the dependent variable. Now, you can draw trend lines on this data, and you can figure out what's known as the R value. The R value tells you how close the data points are to the trend, and the closer they are to the trend, the more likely there is a real effect of the IV on the DV. Okay. So here the data points are pretty close to the trend line. So this would show you that it's pretty likely actually that there might be an effect here of the independent variable on the dependent variable. Similarly, here we have points that are on, there is a trend here, but the points are much further away from the trend line. So that would mean that it's less certain that the independent variable is really the thing that's affecting the dependent variable. There might be other things at play here, other variables that we're not assessing that are causing these data points not to be perfectly on the trend. Okay, and if you were to draw a trend line and there was no movement of the trend up or down, that would tell you that it seems likely there is no effect of the independent variable on the dependent variable. As you increase the independent variable, there is no net increase or decrease on the dependent variable. Okay, that would mean there's probably no effect. And the same for the inverse, you would still have the same convention where the higher the number of the R value, the more likely the correlation, the stronger the correlation. But if it's an inverse relationship where as you increase one, it decreases the other, we just give it a negative sign. So in correlation data, like a negative 0.07 is actually stronger than 0.3, even though it's a negative sign. The negative sign just tells you the direction or the relationship of the variables, whether it be direct or inverse. Okay, so for the exam, if I put these figures up on it, could you tell me which one shows the higher correlation? Like if on an exam, let's say I gave you two different examples here, and one looked kind of like this, and one looked like this. Could you tell me which of these scatter plots, these are called, by the way, XY scatters, because each data point has an X coordinate and a Y coordinate. Okay. If I had these two graphs in there, could you tell me which one has the stronger correlation? And the answer would be definitely this one. Okay, this one, if you were to draw a trend line on there, maybe you could say there's kind of a trend like that, but like these data points are pretty far from the trend line. They're not quite closely, close to the trend line. Here you could draw a trend line sort of like right here, and on average these points are closer to the trend line. So you would say that this has the higher R value, the higher correlation value. Okay, so it's the stronger correlation. A pretty famous study where correlation data was used is the infamous 1854 cholera outbreak in London. And this involves a scientist known as John Snow, who some people call the father of epidemiology, which is the study of how diseases spread. And what happened is there was a pump handle. Back in this day, you didn't just have water plumbed into your house. You'd actually have to go to a neighborhood pump and pump it from the ground. And there was this outbreak of cholera, which is something that makes you really sick and can actually kill you. And John Snow took a map of this neighborhood in London, and this is actually a drawing of his map. And each place there was, I don't know if you can see that, but each place that somebody had died, he drew a little black mark. And you can see that on average, the homes, he kind of looked at this whole map and he said, okay, there's a lot of people dying in this specific part right here. And so it seems to be that there's a strong correlation between the distance from this point here and mortality. And so, like, if he was to draw a map, his variables would be something like this. This would be like the number of people dying, and the distance from Broad Street. And it looked like, as he charted the different homes and how many people died in them, the ones that were closest to Broad Street had the highest number of deaths. And then each of the houses, as the houses get further away, of all the houses he studied, the houses that get further away from Broad Street, the mortality goes down. So there's a pretty strong negative correlation, meaning as you get further away from Broad Street, the mortality decreases. And similarly, if you get closer to Broad Street, the number of people dying increases. Okay, that would be a real graph that he could draw from that map. So that was correlation data. You can't, just make nice on a survey like this on the fly. You can't organize a nice study into discrete groups of people, but you can still wield the scientific method to do something very important. And in this instance, he discovered that they're all really close to this pump. So maybe there's something going on with the pump that's causing the cholera. And so he actually, the next day, he reported these findings, and the next day he took the handle off the Broad Street pump, and people stopped dying. So it showed that the water that was contaminating the population was coming from that well pump. And even today, there is a monument with a handleless pump that stands in the approximate location of where that original Broad Street pump was located in London. Okay, but that was a very valuable insight to be gleaned from the scientific method that used correlation data on the fly in a situation where it was difficult to create a controlled study. Okay, now there are pitfalls to correlation hypothesis testing that comparing means don't have to deal with. And to illustrate this, take a look at this. This is showing the sale of ice cream, and this is showing the forest fires. And there, if you were to plot these together, there is a really strong correlation between these variables because the trends follow a similar pattern. And some people would maybe make the case, man, what is it about the sale of ice cream that's causing forest fires? Or similarly, what is it about the number of forest fires that are really driving ice cream sales up? And so there can be a danger here, and the danger is that correlation does not necessarily reveal causation. Just because two variables are correlated does not necessarily mean that the one causes the other. It can mean that, but you would just want to make sure that you ruled out all of the alternative hypotheses, or as many as possible, and the more that are ruled out, the more likely it becomes that the variables really are causing. And in a situation like this where you have variables that are correlated with one another, the reason why this can happen is that there's usually a third variable that both of the dependent variables are tethered to. So in this example, the third variable would be temperature, likely. Okay, that the sale of ice cream increases as the temperature gets warmer. Also, forest fires increase as the temperature gets warmer because the sale of ice cream is probably dependent on the temperature, and forest fires are also dependent on the temperature. And because these are different variables, this is the sale of ice cream and this is forest fires, but because they're both dependent on the same hidden third variable, they appear to have the same correlation with one another. Okay, this can get into some funny business. So there's an interesting book here written by this guy Tyler Vegan, and I don't know how his last name is pronounced, but it's called Spurious Correlations. And basically his point is that with big data, you can find a correlation with all sorts of things, and this is actually kind of funny. And we said that when you have two variables that follow the same pattern, it could be because of a third variable. The third variable in this case would just be the random luck of the draw that can happen when you're dealing with such an enormously huge data set. Okay, so some of the ones that he found that are humorous: there is a strong correlation between people who drowned after falling out of a fishing boat and the marriage rate in Kentucky. So man, as the marriage rate declines, the people that follow those boats just decline as well. So we gotta save lives and stop having people get married, right? Like that would be an erroneous conclusion from this graph. Okay, there is a strong correlation between the age of Miss America and murders by steam hot vapors and hot objects. So again, a very false interpretation of this would be, man, if we can just get Miss America to be younger always, we can save lives by steam, hot vapors, and hot objects. There's a strong correlation between the divorce rate in Maine and the per capita consumption of margarine. There is a strong correlation between the per capita cheese consumption and the number of people who died by becoming tangled in their bed sheets. Okay, there is a strong correlation between the number of people who drowned by falling into a pool in films Nicolas Cage appeared in. So if we just gotta ban Nicolas Cage from any more acting, because it is killing people as they drown in a pool. People see those films and they can't live any longer, and they end it. Okay, so that would be a false interpretation of this. In reality, these are tethered with one another because of a third variable, a third reason, and the third reason is simply random chance that can happen when you have the world's data sets at your disposal and you're looking for variables that coincidentally align with one another. Okay, so in summary, correlations do not necessarily reveal causation. They can, but you need to maintain a degree of skepticism and rule out all possible alternative hypotheses. Okay, a little bit about scientific theories. Now, what a scientific theory is, it's when a hypothesis has been demonstrated numerous times through numerous ways. We would maybe create a scientific theory, which is a little bit more of a validated claim about the nature of our world. So there's a textbook out there that would define it as the following. It's an explanation for a set of related observations that is based on well-supported hypotheses from several different independent lines of research. So an example, we believe that stomach ulcers, okay, people get stomach ulcers, these painful things in their stomach. We believe that stomach ulcers are due to the growth and proliferation of this specific type of bacterium, Helicobacter pylori. We did not always believe that. So there is now the scientific theory that stomach ulcers are due to these bacteria. 50 years ago, it was thought that stomach ulcers are due to eating too many acidic foods or eating too much fat or whatever your diet has. So that was a scientific theory in that day, and that was well established by lots of numerous explanations and observations. And then that theory sort of crumbled and gave way to this new theory that we have now, this new paradigm where stomach ulcers are formed by Helicobacter pylori. And this was a more recent development. I can't remember the date here, but probably within the last 20 or 30 years. And that was really put forth by these two scientists here, Barry Marshall and Robin Warren. Okay, so now that's a theory. And there's been a lot of scientists who have since corroborated that hypothesis. There's been different studies that have shown it repeatedly that stomach ulcers usually have these bacteria growing in them, and so it's an established set of observations that we regard as sort of the new standard idea about how the nature of stomach ulcers work. It's called the scientific theory. All right, we're going to end here talking about scientific measurements. And what we use to collect data is the International System of Units, or SI units. And to understand why this is important, it would be really frustrating if you were trying to work with researchers in other parts of the world that were all using their own system of measurements. Like, maybe us in America, we were using things like feet and inches and miles to study the distance of something, and then you go into Great Britain or you go into another part of the world and they're using things like meters, and you go into another part of the world and they're using like cubits, different measurements. It would be really hard to look at the data from other people's studies and see how it matches with your data when we're all using these different units. So to sort of streamline the process globally of how science is done, scientists generally agree on the common convention for units, which is known as the International System of Units, or SI units. And it looks something like this. For each dimension of measurement, there is a defined base unit. Okay, so for length, Here's a few different dimensions here of measurement. You can measure things like length or distance, mass, volume, and there's a lot of others too. Like you can measure temperature or light intensity or gas concentration. Lots of different dimensions, pressure, force. But three common ones here are length, mass, and volume. And so the base unit for length is this thing called a meter. It's a defined distance. If I gave you a meter stick, the length of that stick is what we call 1 meter. Mass is the gram. There's a weight that has a certain heaviness to it, and we've defined it as 1 gram. And if I put that in your hand, you would be holding 1 gram, and anything that had the same mass as that thing you're holding in your hand would also be a gram. It is the base unit. Okay, and for volume, it's the liter. It's a defined volume. So the way that it works is that not always is it the case that you can use the base unit. There are times when you want to measure something that's very, very small. So you wouldn't want to use a meter stick. You wouldn't want to use a meter stick to measure the distance or the width of a bacterium. Or similarly, you wouldn't want to use a liter bottle to measure how much volume is in a lake. Okay, you would want there are times when you want to use a different unit than the base unit, and so then you would be required to convert it. And in this convention of units, they have defined conversions, and they are all base 10, which means as you go up and down, it varies by a magnitude of 10. Okay, so for example, you can start off with the base. Let's say I am going with a meter. Let's say I'm measuring a length of something. The base unit is the meter. If I had 10 meters lined up end for end, I would call that not a meter stick, but I would call it a decameter stick. Okay, a decameter would be the length of distance that's 10 times the base. And if I had 100 meters lined up end for end, I could fuse those together, and now I wouldn't have a meter stick, I would have a hectometer stick. A hectometer stick would be 100 meters long. And if I wanted to put 1,000 meters together, now I would have a kilometer stick that I could use to measure kilometers. So we can use these different measurements based on the application of the study. Similarly, if I wanted to take that meter stick and chop it into 10 parts, one of those 10 parts would be called a decimeter stick. And if I wanted to take that meter stick and chop it into 100 bits, 1/100th of that meter stick would be called a centimeter. And then if I took that meter stick and chopped it into 1,000 little bits, and 1,000th of that meter stick, that would be called a millimeter stick. Okay, generally what you do is when you convert to smaller units, you move the decimal to the right, and the number of places that you move the decimal depends on how many columns up or down you went on this convention here. And if you want to use to convert to larger units, then you'll move the decimal to the left. So let's try and practice this. Let's say you have a measurement of 3.8 meters. Meter would be the base unit for length. So we're measuring some sort of length of some kind. And I want to know how many centimeters is equivalent to that 3.8 meters. Okay, well here's the base. Meter is the base. So we're starting here. We have 3.8 meters. And centimeters is over here. And I want to figure out how many centimeters it is. Well, I'm going 1, 2 places. So I'd have to take this decimal right here and move it 2 places. And the question would be, do I move it to the right or to the left? These units are smaller over here, and these units over here are larger. So I would be going to a smaller unit. I would move the decimal to the right, and I would move it 2 places. So you take that decimal, 3.8, you take the decimal, move it 1, 2 spots, fill in a 0 as a placeholder, and now I've got 380 centimeters. So 3.8 meters is the same thing as 380 centimeters. I've just converted from meters to centimeters. Okay, here we have 48 milligrams. So gram here means we're measuring how heavy something is, the mass of an object. And we're starting here in millis, so we're starting right here, the milligram. See that I have the prefix here, m, and I just add the base to it, milligram. And we want to get all the way up to the base, which is gram. Okay, so here's a gram. Well, I'm moving to a larger unit, so I would want to take that decimal place, which is hidden in this number here, but I want to take this decimal right here, and I want to move it, to the left, because I'm going to a larger unit. These are larger, these are smaller. How many times do I move the decimal? Well, that depends on how many columns up on this convention I go. So I'm trying to get to the base, which is gram. I'm starting with milligrams, so I got to go 1, 2, 3 spots to get to the base. So I'm going to take this, I'm going to go 1, 2, 3. Fill it in with zeros. So 48 milligrams, oh, sorry. I want to go to the left, not the right. Okay, so just disregard what I just did. I want to go the other way. I want to go left. 1, 2, 3. Fill in with a 0. So 0.048 grams is the same thing as 48 milligrams. Okay. All right, here I have liters, the base for volume, and I have deciliters. And I want to get to milliliters. Okay, so we're starting with a deciliter. Here we have D. And we want to get to milli, which is the one with M. So I have 48 deciliters. I want to get to milliliters. So we're going to go 1, 2 spots. We are getting smaller. So the decimal has to go to the right. So we'll take 48. Here's the decimal point. Move it over 1, 2. So 48 deciliters is actually 4,800 or 4,800 milliliters. Okay. This is something you're going to have to be able to do on the exam. I'm going to give you questions that look a lot like this. And so if you don't feel like you can do this, make sure you come and visit me. I can give you some practice problems. We can jump on a Zoom call and we can practice these until you feel comfortable. This is going to be another big hurdle for the next exam. Okay, so that's sort of going to wrap up here our discussion of science. The big wrap up here is that science is heavily dependent upon the scientific method, which is a tool that helps us reduce our bias. We all have bias, and completing the perfect experiment and interpreting the data with a complete objectivity is almost impossible. And definitely for me too. Like you'll see I have bias that creeps in. Like I have a lot of bias about the whole conversation with evolution, because I believe that God created the world, and so anytime I hear things saying that we just spawned out of a pool of bacteria without any divine will or power, I have a lot of bias there. And so I will always, with my bias, exclude some of the findings that come from those types of studies. So we all do have it. It's really impossible to be perfectly objective, but as scientists we strive to do as good of a job as we can, and that's where we strive to hold high the scientific method, because that really helps us design experiments which will reduce bias. Okay, so that is the nature of science. For the exam, you want, like I said earlier, to be able to if I give you a scenario, like a snapshot of a scientific study, can you tell me what the dependent variable is, the independent variable, what the hypothesis might be, what the control variables would be, the control. I've got practice problems to help you do that. That's a big thing you want to be able to do. For statistics, you want to know what a p-value is, and you want to know what it incorporates, and it incorporates how the sample size and the sample spread, and a lower p-value means that any difference in averages that you see between groups is more reliable. Smaller the p-value, the more reliable the difference that you see is. You want to know a little bit about correlations, that they're used when you can't control an experiment very well. They're used when there might be multiple variables that you're looking at, and they can be somewhat, you need to be a little wary with them because they don't always tell you about causation. And if I drew a chart that showed data points, could you tell me if it was a strong correlation or a negative correlation with the trend? You put a trend line on that data, which of the graphs has the stronger correlation and not, and which one has the weaker correlation? Okay, could you do that? And then lastly, if I put some units on there, can you convert them? And can you tell me what the base units are in the metric system, the SI system, for mass, length, and volume? Those are your big tasks for Chapter 1. Okay, welcome to science, and from here we will get a little further on specifically into talking about biology. But before we get specifically into biology, a nice survey of what science is and is not, I think, is helpful. And we even now have some skills to put in our tool bag for the rest of the course and the labs that we will be diving into.